The universe is a vast and mysterious place. We can gaze at the stars and wonder about their origins. But what are the fundamental laws that govern the universe? This is the realm of quantum physics, a world where reality takes on a bizarre nature. Quantum physics studies energy and matter at atomic levels. Particles can be in multiple states at once. Information can travel faster than light. Observation influences reality. It challenges our intuition, yet it underpins revolutionary technologies. What is the universe made of? To understand the quantum world, we must first delve into the heart of matter. Everything we see, touch and feel is made up of atoms. Atoms, once thought to be the smallest indivisible units of matter, are themselves composed of even smaller particles. These particles, known as subatomic particles, include protons, neutrons, and electrons. Protons and neutrons residing in the nucleus of an atom give an atom its mass. Electrons, much lighter and orbiting the nucleus at incredible speeds, determine how atoms interact with each other. This interaction leads to the formation of molecules, the building blocks of all substances. But the subatomic world is far from the neat and orderly picture of orbiting planets often used to depict atoms. Here in the quantum realm, particles behave less like tiny balls and more like waves spread out over space. This wave-particle duality, where particles exhibit both wave-like and particle-like properties, is one of the central mysteries of quantum mechanics. It challenges our classical intuitions about the nature of reality. How can something be both a particle with a defined position and a wave spread out over space? This question puzzled the greatest minds of the early 20th century. The seeds of quantum physics were sown in the late 19th and early 20th centuries. Physicists like Max Planck, Albert Einstein, and Niels Bohr made groundbreaking discoveries that challenged the foundations of classical physics. These pioneers revealed that energy, like matter, is not continuous, but exists in discrete packets called quanta. This discovery, a radical departure from classical physics, marked the birth of quantum mechanics. It opened up a Pandora's box of scientific inquiry, revealing a universe stranger and more wondrous than anyone had ever imagined. One of the most profound and unsettling principles of quantum mechanics is Heisenberg's uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we try to measure one, the fuzzier the other becomes. This isn't a limitation of our measuring tools, it's a fundamental property of the quantum world. Imagine trying to pinpoint the exact location of a wave on the ocean. You might be able to mark its crest at a given moment, but its momentum, the way it's moving, is spread out over the entire wave. In the quantum realm, particles behave like waves, and their position and momentum are intrinsically linked. This inherent uncertainty is not due to any lack of information or precision in our measurements. It is woven into the very fabric of reality at the quantum level. Another mind-bending concept in quantum mechanics is superposition. In the classical world, an object can be in one state or another. A light switch is either on or off. A coin toss results in heads or tails. However, in the quantum world, particles can exist in multiple states simultaneously. Imagine a spinning coin that is both heads and tails at the same time until we stop it and observe the outcome. This is akin to how particles in superposition exist in a probabilistic haze of multiple states. It's only upon measurement that the particle collapses into a definite state. This doesn't mean that the particle was always in that particular state and we just didn't know. It means the act of measurement forces the quantum system to choose a specific outcome, altering the reality we observe. One of the earliest discoveries that led to the quantum revolution was Max Planck's explanation of blackbody radiation. Classical physics failed to explain why heated objects emit specific colors of light. Planck, in a revolutionary proposal, suggested that energy was not continuous but came in discrete packets or quanta. Imagine a guitar string that can only vibrate at specific frequencies to produce distinct notes. Similarly, atoms can only absorb or emit energy in specific amounts, corresponding to different energy levels. This quantization of energy explained the spectrum of light emitted by heated objects. This discovery, though seemingly simple, had profound implications. It shattered the classical view of energy as continuous and laid the foundation for understanding the behavior of atoms and molecules. One of the most intriguing phenomena in quantum mechanics is quantum tunneling. Imagine throwing a ball at a wall. In the classical world, the ball would either bounce back or, if it had enough energy, break through. However, in the quantum world, there's a chance the ball could pass straight through the wall as if it wasn't even there. This is because particles behave like waves, and waves can spread out and even penetrate barriers. The probability of tunneling decreases exponentially with the thickness of the barrier, but it's never zero. This bizarre effect is not just a theoretical curiosity, it's the reason our sun shines. Quantum tunneling is essential for nuclear fusion, the process that powers stars by allowing protons to overcome their mutual repulsion and fuse together. Planck's constant, a tiny seed of revolution. The story of quantum physics begins with a whisper. Max Planck tackled the black-body radiation problem. Classical physics failed to explain heated objects' radiation. Planck proposed energy is emitted in quanta. Energy is absorbed in discrete packets, not continuous flow. Each quantum is proportional to frequency times Planck's constant. This constant, h, unlocked the quantum world. Energy, like matter, is not infinitely divisible. This idea laid the foundation for a revolution in physics. Einstein's light quanta in action. A few years after Planck's revolutionary proposal, a young Albert Einstein, then a patent clerk, recognized the profound implications of quantized energy. In 1905, Einstein published his groundbreaking paper on the photoelectric effect, a phenomenon where light shining on a metal surface could eject electrons. Classical physics couldn't explain why this effect depended on the frequency of light rather than its intensity. Einstein, drawing upon Planck's idea of energy quanta, proposed that light itself was composed of discrete packets of energy, called photons. Each photon carried an energy proportional to its frequency, as dictated by Planck's constant. Einstein's explanation of the photoelectric effect not only earned him the Nobel Prize in Physics in 1921, but also solidified the concept of light as both a wave and a wave-particle duality that became a cornerstone of quantum mechanics. Bohr's atom, a quantum leap in understanding. While Planck and Einstein were revolutionizing our understanding of light and energy, another giant of physics, Niels Bohr, was tackling the atom. In 1913, Bohr proposed a model of the atom that incorporated quantum principles to explain the stability of atoms and the discrete nature of their emitted light. Bohr's model, a radical departure from classical physics, depicted electrons orbiting the nucleus at specific energy levels, much like planets orbiting the sun. However, unlike planets, electrons could only occupy these discrete energy levels, and they could jump between them by absorbing or emitting photons of specific energies. Bohr's model, though later refined by quantum mechanics, provided a crucial stepping stone in our understanding of the atom. It elegantly explained the spectral lines of hydrogen and other elements, patterns of light emission unique to each element that could not be explained by classical physics. Section 4, the Solvay conferences, a meeting of minds. The development of quantum mechanics was not a solitary endeavor. It was fueled by a collaborative spirit, a meeting of minds that grappled with the bizarre and counterintuitive nature of the quantum world. One of the most famous gatherings of these scientific pioneers was the Solvay conferences. Initiated by Belgian industrialist Ernest Solvay in 1911, these conferences brought together the leading physicists of the time. The 1927 Solvay Conference, arguably the most famous, witnessed heated debates between Albert Einstein and Niels Bohr on the interpretation of quantum mechanics. These conferences, though marked by disagreements and unresolved questions, played a crucial role in shaping the course of quantum physics. They fostered collaboration, challenged assumptions, and pushed the boundaries of scientific understanding, laying the groundwork for the development of a complete theory of quantum mechanics. Section 1. Entanglement, spooky action at a distance. Perhaps the most baffling and controversial phenomenon in the quantum world is entanglement. Imagine two particles once intertwined, now separated by vast distances, even light years. Entanglement suggests that these particles remain connected in a way that defies classical physics. Imagine two coins flipped simultaneously, one landing on heads, the other on tails. In the classical world, we wouldn't think twice. But in the quantum world, two entangled particles are like those coins. Their fates intertwined even when separated. If we measure one particle and find it in a particular state, we instantly know the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, suggests that information might be transmitted instantaneously, seemingly violating the cosmic speed limit of light. It's a concept so bizarre that even Einstein, one of the founders of quantum theory, couldn't fully accept it. Section 2. The EPR paradox challenging quantum reality. The strangeness of entanglement led Albert Einstein, Boris Podolsky, and Nathan Rosen to formulate the EPR paradox in 1935. They argued that if quantum mechanics allowed for entanglement, it must be an incomplete theory. Their argument hinged on the idea of local realism. Local realism posits that objects have definite properties independent of observation, and that no influence can travel faster than light. The EPR paradox suggested that entanglement violated one of these principles. Either quantum mechanics was incomplete, missing some hidden variables that explained the correlations between entangled particles, or it violated the principle of locality. The EPR paradox wasn't meant to dismiss quantum mechanics, but to expose its seemingly absurd implications and prompt a search for a more complete theory. It was a challenge to reconcile the bizarre predictions of quantum mechanics with our intuitive understanding of how reality should work. For decades, the EPR paradox remained a philosophical debate, a clash between the counterintuitive predictions of quantum mechanics and our classical intuitions. However, in 1964, physicist John Bell proposed a way to test the validity of entanglement and the EPR paradox through experiments. Bell's theorem, formulated in a mathematical inequality, provided a way to distinguish between the predictions of quantum mechanics and those of any theory that adhered to local realism. If experiments violated Bell's inequality, it would mean that the bizarre predictions of entanglement were real, and that local realism couldn't fully describe the quantum world. In the decades that followed, numerous experiments using photons and other entangled particles consistently violated Bell's inequality, confirming the predictions of quantum mechanics and the reality of entanglement. These experiments, hailed as some of the most profound in scientific history, demonstrated that the universe is far stranger than we had imagined. The implications of entanglement extend far beyond the realm of theoretical physics. It challenges our very understanding of the nature of reality, suggesting a universe interconnected in ways we are only beginning to comprehend. If particles can be linked across vast distances, does it imply a deeper level of connection within the fabric of space-time itself? The study of entanglement has also opened up exciting avenues in quantum information science. Entangled particles are being harnessed to develop secure communication channels, ultra-precise sensors, and even quantum computers capable of solving problems intractable for classical computers. While entanglement remains a mind-boggling concept, its experimental confirmation has revolutionized our understanding of the quantum world and opened up new frontiers in science and technology. It serves as a stark reminder that the universe is far stranger and more wondrous than our classical intuitions might suggest. Imagine a computer so powerful that it could solve problems in minutes. Problems that would take classical computers billions of years to crack. This is the promise of quantum computing, a revolutionary technology poised to transform fields as diverse as medicine, materials science, and artificial intelligence. While classical computers store information as bits, which can be either 0 or 1, quantum computers employ qubits. Qubits, leveraging the principle of superposition, can exist in a combination of 0 and 1 simultaneously. This allows quantum computers to perform computations on multiple possible values at once, exponentially increasing their processing power for specific types of problems. Imagine searching for a specific grain of sand on a beach. A classical computer would have to examine each grain one by one. A quantum computer, on the other hand, could analyze all grains simultaneously, dramatically speeding up the search. This ability to explore multiple possibilities at once is what gives quantum computers their unparalleled computational power. In an age of ever-increasing cyber attacks and data breaches, the need for secure communication channels has never been greater. Quantum cryptography, leveraging the principles of quantum mechanics, offers a way to transmit information with unprecedented security. One of the most promising applications of quantum cryptography is quantum key distribution, or QKD. QKD exploits the principles of entanglement and the observer effect to create a secret key known only to the sender and receiver. Any attempt to intercept or eavesdrop on the key would inevitably alter the quantum states of the entangled particles, alerting the legitimate users to the breach. Imagine two people trying to share a secret message written on a soap bubble. If anyone tries to intercept the bubble, it would pop, alerting the sender and receiver. Similarly, in QKD, any attempt to intercept the key would leave an unmistakable trace, ensuring the security of the communication channel. Quantum mechanics, with its focus on the subatomic realm, might seem a world away from our everyday experiences. Its principles develop sensitive sensors for medical diagnostics and earthquake prediction. Quantum sensors exploit extreme sensitivity to external influences. Atomic clocks measure time with astonishing accuracy using quantum properties. They detect subtle changes in gravity or magnetic fields. Imagine a spider web detecting the faintest breeze. Quantum sensors register slight perturbations, opening new frontiers in measurement. For decades, quantum mechanics was confined to the realm of physics, explaining the behavior of subatomic particles and the interactions of light and matter. However, recent discoveries suggest that quantum phenomena might play a role in biological processes, blurring the line between the quantum world and the world of living organisms. One area of active research is photosynthesis, the process by which plants convert sunlight into chemical energy. Studies suggest that quantum coherence, the ability of quantum systems to exist in multiple states simultaneously, might be involved in the efficient transfer of energy during photosynthesis. Imagine a wave of energy traveling through a network of molecules without losing any of its intensity. This is akin to the coherent transfer of energy observed in photosynthesis, suggesting that nature might have already harnessed the power of quantum mechanics to optimize this essential biological process. As we've journeyed from the heart of atoms to the frontiers of technology, one thing is clear: quantum physics is not merely an esoteric branch of physics, it is the foundation upon which our universe is built, challenging our classical intuitions. Quantum mechanics forces us to rethink our place in the cosmos. It shows us that observation can influence reality. Like a tapestry, quantum physics reveals its beauty and complexity from a distance. Despite its successes, quantum physics is still full of mysteries. One major challenge is finding a unified theory of physics. Quantum mechanics and Einstein's relativity remain incompatible. Reconciling them is a holy grail of modern science. The interpretation of quantum mechanics is another active research area. What does it mean for a particle to be in multiple states at once? These questions fuel the imaginations of physicists and philosophers. The journey into the quantum realm is not for the faint of heart. It is a journey that challenges our deeply held intuitions about the nature of reality and forces us to confront the limits of our understanding. But it is also a journey filled with awe, wonder, and a profound sense of the unknown. Quantum physics has revealed a universe far stranger and more interconnected than we could have ever imagined. A universe where particles can be in multiple states at once, where information can seemingly travel faster than light, and where the act of observation plays a fundamental role in shaping reality. As we continue to explore the quantum realm, we are likely to encounter even more baffling and counterintuitive phenomena, but with each new discovery, with each step further into the unknown, we come closer to unraveling the deepest secrets of the universe and our place within it. The quantum revolution is not over, it has just begun.